But in particular, we tried it in the games of chess and shogi, which is Japanese chess, another very challenging game, as well as the game of Go. And so the main idea of AlphaZero, and the reason it's called zero, is that it learned from first principles. The zero represents here zero human knowledge. The idea that we didn't put into it any human domain knowledge, so it didn't know anything about the game of Go when it was playing Go, apart from the rules themselves. It didn't know anything about chess when it was playing chess, apart from the rules themselves, and similarly for Japanese chess, for shogi. In addition, it didn't receive any human data. It learned solely by playing games against itself and learning by reinforcement learning, starting from random play. And it used no human features. There was no human engineering of the features. No one said, hey, this is a really good shape for the system to take. It only took the raw orders and input. And by making it more general in this way, we also make it more applicable to many domains. There's no special treatment for playing Go. It doesn't, for example, the symmetries of the board or any other special thing you can think of. And if we take away those special cases, we actually make the system much more generally applicable. So how did it work? Well, the main idea was really to try and find the best possible teacher for AlphaGo to learn from, for AlphaZero to learn from. And that best possible teacher is actually itself. So the idea is the following, that AlphaZero plays games against itself. So you see here like a little mini game of Go here, where it starts off in this position here, the empty board position, and it runs a search using its kind of current policy network and value network to guide the search, to kind of reduce the complexity of that search. But at the end of it, it selects a move. And it plays that move, and it runs another search, and it plays another move, and it runs another search, and it plays another move. And what you have to appreciate is that when it runs this very deep search, the search itself is improving the kind of action selection that AlphaZero is using far beyond the initial move selection procedure that's represented by the policy network. And that policy improvement is the heart of this learning algorithm that we used in AlphaZero. So AlphaZero plays games against itself, and we record the outcome. We see whether black or white, in this case maybe black or white. Once we have that outcome, we train a new policy network to predict AlphaZero's moves. So in a sense, what we're doing is we're saying, well, we were in this position and we ran our search and it suggested that we should play this move. So now we're going to train our new policy network to play the same thing that AlphaZero with search actually played. So we're going to try and distill the whole of this search, this really deep search that we're doing with all these kind of look ahead. So we're basically combining the neural network with look ahead search, and that's outputting this improved action selection policy. And now we're going to distill that back down into the neural network and say, let's get this neural network to predict what the search does, predict the move that's picked when you actually run this deep look-ahead search. So you do all this planning, that outputs your best possible move selection, now predict that thing, that becomes your teacher. And so we do that for each of the moves that we encountered during self-play, and that gives us a new policy network. At the same time, we train a new value network to predict the winner of those games of self-play. So again, we play these very high-quality games between AlphaZero, not just the policy network, the raw policy network playing against itself, like in the original AlphaGo. These were actually using search to improve the policy, run our best possible action selection procedure. Really think, look ahead, use your thinking time, and then pick actions. And at the end of that, we get a very high-quality estimate of who the winner of that game actually is, and we're going to train the value network to actually predict who the outcome of that very high-quality game will be. So again, AlphaZero itself becomes the teacher. And once we have that, we have a new policy and value network, and that gives us the next iteration of AlphaZero. So we can now iterate this procedure as many times as we want. We arrive at a new policy and value network, and that results in a stronger search, that results in better move selection, that results in higher quality data, higher quality outcomes to those games, and then we cycle that back round indefinitely. So that's the AlphaZero training procedure. How it works there. Okay, so how does it work? Well, what we found was something remarkable happened. Remember, we've taken away the extra knowledge that we were putting in before. We've actually taken something away. We've taken away the human data. We've taken away any form of human knowledge that was put into the system, like even things like symmetries about boards and all these kind of things. And we found that it was still able to not only reach the performance of the previous AlphaGo, but dramatically exceed it. So after around 8 hours of training, we found that it was able to defeat the original AlphaGo system. And at the end of training, it was actually able to defeat the original AlphaGo by 100 games to 0 in test matches. So the maybe moral here is that by making the system more general, we take away our human biases as to what's effective or not. We take away the reasons that were leading it to perhaps misjudge things, and we force it to evaluate things for itself and to understand the system for itself better and better and better, until ultimately, when we actually played this online against the top human players in the world, we won 60 games to 0. So we also found that this system was able to discover new kinds of human Go knowledge. So if we look at these different opening positions, we see that over time, during training, it actually starts to discover these kind of opening sequences. These are like the opening sequences that human players actually use in the game of Go. And it discovered them, one after the other. It found these very, very famous, well-known sequences that humans like to play in their openings. But eventually, it actually discarded some of them in favor of its own opening sequences that it had discovered, which it considered to be superior. And actually, certain human professionals are now using AlphaGo's openings instead of their own. Okay, so we also applied AlphaZero to the game of chess. And chess is arguably the most studied domain in the history of AI. This was studied by all of the seminal figures in AI actually studied computer chess. Babbage, Turing, Shannon von Neumann, they were all fascinated by computer chess. And it was considered the Drosophila of artificial intelligence for several decades. And so chess is interesting to us because it has the most highly specialized systems in the world because of all this dedicated effort that's being applied to the game of chess. And so in 1997, Deep Blue was able to defeat the human world champion, Garry Kasparov. But since then, what maybe some of you don't know is that this amazing progress continued to happen beyond that, until the state-of-the-art programs now, such as programs like Stockfish, are indisputably superhuman, vastly superhuman. We also considered the game of Japanese chess, shogi, which is actually more complex than chess, because it has a larger board and a larger action space. In fact, when you capture a piece, you have a special move, which is you can place that piece back down on the board as one of your own. And so this really leads to enormous tactical complexity, and actually programs only recently reached human world champion level for the very first time, about a year or two ago. And for all of these cases, for all of these versions of chess and similar games, the previous state-of-the-art engines were based on something called AlphaBeta search, using these very powerful handcrafted evaluation functions that are being optimized by human experts and human grandmasters, and often using a lot of very general techniques, but also a lot of game-specific heuristics as well. And so if we look at the anatomy of a particular world champion chess engine, we consider the previous world champion Stockfish, which actually won 3 out of the last 4 TCEC world championships. We see that it had this huge amount of knowledge that had been put in there. And if you look at it, I don't have time to go through all these different pieces of knowledge, but I can say that every single one of these you can think of as like a breakthrough in the history of computer chess. That was probably the equivalent of someone's PhD thesis to figure out one of these things and come up with a new technique that then actually made those chess programs much stronger. And Stockfish is not the first to use these, but perhaps represents the most elegantly programmed version of computer chess that was able to put all of these ideas together and achieve enormous performance. And so what we tried doing with AlphaZero was to get rid of every single one of those. And so we didn't use a single one of those techniques. Instead, we used exactly the system which I already described, self-play reinforcement learning, combined with the kind of search we talked about earlier, this multi-color search approach, which is also based on self-play. And that's it. There was no AlphaBeta search, there were none of these heuristics, and the question is, how well did it perform? And the answer is that it actually outperformed Stockfish. So it was able to defeat Stockfish after around 4 hours of training by self-play. Now I should point out that when I say 4 hours, this was of course 4 hours on quite a lot of custom Google hardware, so it would take a little longer if you were to run this on your desktop. But nevertheless, I think it's an interesting result. And at the end of training, when we played our evaluation games, we played 1,000 games to get a lot of draws in high-level chess. But at the end of 1,000 games, AlphaZero won 155 games, and Stockfish just 6 games. And the story in shogi was even more compelling, which was that AlphaZero beat the world champion program Elmo after 2 hours, and at the end of training won 911 games to 77. So what do we learn? Well, I think the lesson is that general systems carry power. That the more general you make your system, it feels like you're giving something up. But each time you put a little bit of knowledge in there, you're actually harming the ability of your program to discover things for itself. And if you can find a mechanism by which an algorithm can learn for itself those same ideas, then it can also go further than those ideas. And so let's invest our energy in the systems which actually can discover knowledge for themselves, rather than perhaps into us putting the knowledge into the system. And maybe that's it's not that these other systems can't be successful, but perhaps this has more legs in the future. Okay, finally I want to talk about our most recent work, which is in the game of StarCraft 2, and in particular our program AlphaStar. So, what is StarCraft? Is there a slide here? Okay. So StarCraft is a game in which it's a real-time strategy game, in which you have to gather resources and then use those resources. So you kind of build these units that go and mine resources, and you use those resources to kind of build up your technology tree, to advance your technology, and ultimately use that technology to try and defeat your opponent. And there's enormous complexity to this game. Indeed, among video games, it's considered to be at the peak of human ability. If you ask human video gamers, serious esports players, what's the hardest game? Most of them would say, that over the last 20 years it's been StarCraft. And it's canonical, it's been played by millions, and it's endured 20 years of active human play, prize pots in the millions, hundreds of thousands of players still active today if you go onto these online mappers. And from a research point of view, it's been resulted in hundreds of submissions. Again, a lot of this work actually started here in Alberta. Over 12 years of competition, starting with these different competitions, using actually this is the Alberta system here, and these are various different competitions that have been run in the years since like 2006. There are many overlapping competitions, and so it's become something of a benchmark for these kind of high-end artificial intelligence systems that are able to play the canonical video game. But from an AI point of view, what's interesting? Well, the complexity is immense. I mean, if we talked about the large action space in Go, we saw that video that kind of showed how this thing grew. Well, in AI, in StarCraft, the action space is something like 10 to the 26 per step. That there's, you can think of this as like a giant game of chess with hundreds of units on each side. And for each one of those moves, you get to play an action, one of hundreds of different kinds of actions, and each of those actions can do something to any subset of your own units. So it's like you get to kind of play a move where you move kind of 17 different pawns over to some particular location on this huge map. And you can pick any of the 17 pawns you like. Okay. And there's also a long planning horizon. There's something like 15,000 steps on average until the game is either won or lost. And at the end of that, you just get this one bit of information, which is you won or you lost. Now go back and figure out whether what you did was a good idea 15,000 steps ago. And there's also very impoverished information in two particular ways. So first of all, there's something called fog of war, which means that you only see opponent units within range of your own units. So if your units are outside, if your opponents are beyond your own units, if they're kind of outside the line of sight, close to your own units, you've got no idea they're even there. You've got no idea what your opponent's doing. Over the vast majority of the map is kind of unseen by you. In addition, you have to kind of click and move your own camera view around, and you can only actually view and control units that are on screen. And there's also hard game theoretical challenges. In particular, it's like this giant game of rock, paper, scissors, in that every strategy has a counter strategy, partly by design, and partly by discovery by pro players and tuning of the game over 20 years. Blizzard, the makers of the game, continue to tune this to make sure that there's no dominant strategy. And for every strategy, there's something else you can do that defeats it. Flying units versus ground units, one race beats another race, and so forth. Okay. And for this initial work I'm going to talk about, and I'll come back to this, but we decided not to tackle this active camera view challenge. So we presented the agent with a full view of the whole map, but it still had to do with fog of war, so this was still an imperfect information game. It couldn't see what the opponent was doing, unless it was actually within view. Okay? So let's start off by trying to understand what does pro play look like in this game. Why is this considered hard? So pro players are kind of amazing at this. Sorry about that. This is what they look like. They're kind of clicking several hundred times per minute And each of those clips is like a meaningful action where they've actually trained, like one of the players who played this, he's been playing this game since he was 4, non-stop pretty much, many hours a day, and he's worked out these kind of master strategies. And each one of these clips is kind of actually, doing something quite sophisticated, so there's a lot of strategy going into this game. It's not just like a dumb clicking game. So there's kind of several hundred meaningful clips per minute. So we set out to tackle this, and to understand the system, I'm going to start by showing you the anatomy of our agent. So this is maybe best understood by looking at the screen. So this is kind of showing you what's going on in the world. This is actually not us moving the camera around yet, and we'll come back to that. But roughly speaking, what you see here is that we receive raw observations from this game screen. And those raw observations are basically telling us the list of units that we can see across the whole map and the attributes of those units, but only for those units which are not hidden by fog of war, only for those units which are actually viewable by us. So there's all these units which are kind of hidden behind the fog, and you just can't see those at all. Okay, and you see this kind of thing flashing over here. So if you see this flashing, this raw observation, that means that we're actually not only picking the action to play, we're also picking how long to wait until we next poll the observation. So we kind of pick this like macro action, which says, do something, and then wait like 10 steps until you get to do something again. And so that's like this temporal abstraction that allows us to kind of deal with these 15,000 steps by kind of reducing it to a smaller decision space. But we pick how often to do that. So then all that information gets fed into a very sophisticated neural network. I'm not going to describe the actual architecture, but for those of you who care about these things, it uses a lot of attention. It's an attention-based neural network that gets to attend to different units and, using a transformer-style architecture. It's got a recurrent neural network, and at the end of it, it's got an attention-based kind of mechanism that it uses to actually pick the action. And so the action it picks is like this compound action that has many parts to it. It first of all picks which particular kind of action to use, and that's this decision over here, which is basically highlighting, am I going to pick to do a move action, or an attack action, or a build action, and there are several hundred of these different kind of candidate action categories to use. And then for each of those categories, it then decides, which location should it apply that action to, and which unit should it apply that to. And there's like about 13 different steps to constructing this action kind of auto-aggressively, piece by piece by piece. And this is kind of showing the heat map over locations. And in addition, we also have something like a value network that's estimating who's going to win the game, and that value network actually makes use of opponent information as well to reduce variance. So that's roughly the kind of the architecture we use. But what's really going on with this system? How do we train it? Well, to train it, we use something we call the AlphaStar League. And so roughly speaking, this is made up of the following pieces. So each agent, every agent in this system is kind of like, think of it as one of these AlphaStar instances. And each agent is playing games during training against other agents and their past selves. And the fact that they're able to play against their past selves, you can think of this as a way to guarantee learning progress without cycles. It kind of prevents it from forgetting the strategies that were previously successful. You can think of this as a form of a fictitious play for those who know about game theory. And we train these agents initially by supervised learning from strong human games, and that helps to sidestep some of the hard exploration difficulties of even just finding a strategy that uses some of these sophisticated abilities that exist within the game. But it was trained subsequently purely by reinforcement learning, basically by having to learn to beat a given mixture of opponents. So for any given mixture of opponents, we sample the opponent, we play games against that opponent, and we update the agent to be able to beat that opponent more effectively by reinforcement learning, specifically by following the gradient of the policy gradient reinforcement learning. And in addition, one thing which was unique to the AlphaStar League was this idea that agents were encouraged to play a wide diversity of counter strategies. And this was how we dealt with this kind of huge space that you have of strategies and counter strategies in the game of StarCraft. So these were initialized from human play, but then we additionally had diversity by specializing against particular agents, by learning how to defeat, agent number 1, or learning how to defeat agent number 2, or by using what we call build order specific incentives. So these were pseudo rewards that were learned from data, and those pseudo rewards were basically asking it to mirror particular openings that was used by human players, according to the data. And so we combine these additional incentives for diversity into the system, and all of these agents were then playing against each other in the league and learning how to do better against each other, but against this quite diverse array of possible strategies that we used. And what we saw was that over time, we initialized this system from then community replays, and at each step we have these agents in the league, which are used to play against. So we now have these games that are played against all the different samples from other agents in the league. These are the different competitors we play against, and we play games against those different competitors, and that leads to kind of new strategies. And those new strategies we play against the old strategies that we had before, but also against the new strategies that we found. That leads to new strategies and so forth, and the league progresses and gets stronger and stronger and stronger. And when we put this system together, we then choose the agent that we're going to play at the end, and we evaluated that agent against human players. And so let's see how well this did in practice. So this plot shows that we were kind of rising in our estimated performance, starting from our supervised learning estimates here. These are different kind of iterations of training in the league, like all of the different agents over all of the different iterations that we saw. And we estimated their MMR, which is the ranking system used internally by StarCraft players, something like an ELO rating. And we saw that steadily rose over time. And we estimated the two players that we were going to play against, TLO and Mana, two strong human professional players around here and here. So according to our internal estimates, we were doing better, but of course that you never really know until you play them. We also saw that we were making monotonic progress with respect to what we'd seen before in this league. This idea of kind of robustifying ourselves by playing against our memory of all of our previous past selves was really helping in the sense that, so this plot shows you essentially the dominant strategies, which is computed by finding the Nash equilibrium at each iteration. So the dominant strategies, which strategies were dominating the other strategies at each iteration of the league. So the iterations, the training time was going along here, and at each stage we see that the dominant strategies are coming directly from this frontier of training. But we never ever found it useful to go back to some kind of old strategy and use that. It was kind of, all of these old strategies here were strictly dominated by the new ones along the frontier. So we're really finding a strategy that was making monotonic progress in that sense. And this is simply saying that we were moving around a lot in strategy space. This is a kind of embedding of where we were in strategy space. We saw these agents really developed a lot and changed a lot over time during training in terms of the kind of units that they played. Okay, I'm sure what you really want to know is how we did against pro players. And I have this little video that shows us actually watching the game. You can kind of see our reactions at the very first time that we played AlphaStar against humans. Sorry. Let me try that again.
Why haven't we seen a pro play StarCraft up close? I don't understand how you can hit 800 times, let alone doing 800 useful things.
So this is us embarrassing ourselves and making fools of ourselves watching. Okay, so that was the first victory. And rather than go through all of that, so the final results were that we won 5-0 against TLO, who was a top 16 player in the North American ladder. He was a stronger player in general, actually, but we asked him to play his unfavored race. In the game of StarCraft, there were 3 different races. We were playing just one of them, Protoss. So then we played against a top Protoss player who really was playing his correct race, this guy called Mana, and he really is a top 5 player. One of the top professional players in the world, been training since he was 4, as I mentioned, and we won our initial games 5-0. We played one additional game live on a live stream, and we actually lost that game. And what was special about that game, apart from us playing live, was that we actually went back to this question of could we address the one final way in which we weren't playing according to the way humans played, which was to actually be able to move the camera around in the way that humans move the camera around, and actually, attend kind of like moving your eyes around as a person, and kind of have this foveal focus. Could we get StarCraft, our agent, to actually focus on the correct parts of the screen and learn how to move its focus around and pick actions in exactly the way humans were forced to, with this kind of economy of attention, where you have to invest your attention in the right places to be able to learn where to actually even gather your information and apply your actions. So the first time we tried that, we lost. And that led us actually to further research, which is ongoing. But I can announce that we're actually having, in the coming weeks, we've actually announced that we are playing online over the coming days and weeks on Battle.net to actually evaluate these new agents. And this is actually playing a full game of StarCraft, so using this camera view and this attending and moving around in the way that humans do. We're playing all 3 races against all 3 races, so 9 possible race matchups compared to the one that we tried before. All ladder maps, so in the way that you get to pick ladder maps online, and with much more restricted actions per minute. So after we evaluated the agent I showed you before, there was some criticism from the community that we were still clicking a little bit too fast compared to what humans could do in certain situations, and so we tried to address that as well. So results to be announced too. So I just wanted to finish by saying, we've talked about games, and I hope I've convinced you in some small way that the games are an interesting testbed for understanding artificial intelligence and for validating the performance of our systems, and that furthermore these self-learning systems based on reinforcement learning and deep learning combined together have a lot of power. But of course, a deep mind where I work, but of course the research community in general, we want to know that these techniques can have impacts beyond games. And so I thought I'd just mention one recent success story, which is perhaps more on the deep learning side than the reinforcement learning side, although it still borrows many of the ideas I've mentioned. You can think of the search tree now being replaced by a kind of simulated annealing style search, and but still learning things like these neural networks to estimate how well you're doing in each of these situations.